So, good morning once again to everyone. So, in the last class, we started talking about memory systems and we talked about the memory hierarchy, how we use different types of memories, fast memories, large memories, and connect them in a hierarchy to get the illusion, provide the illusion to the CPU that we have a large and fast memory at the same time, right? So then we started talking about the cache memory design part of it, and we talked about different things. We talked about temporal and spatial locality of programs in programs that we exploit to get the desired performance effect out of a memory hierarchy. And the last thing we discussed was how a direct map cache works when a read access is happening. So let's resume from there. So we had the design or the structure of the direct map cache like you see on the screen. And so the cache itself contains this light gray area, right? An array of data blocks, mind you, not words, data blocks, and an array of tags for each of those blocks, and an array of valid bits. The indices we used to access this, but the indices are not stored. It's just for our convenience that we mark the indices here, index column here. Right. So what happens when you receive an address? We divide the address into three parts. Offset tells us which word or byte we are looking for in the data block, within the data block. Index part of the address depends on the size of the cache, the number of cache entries we have, and that tells us which entry we are going to access. So that is the key feature of direct map, where a given memory block has only one place that it can be mapped in the cache, right? So the index part tells us what that place is, and the tag part of the address is stored along with the data, and we have to compare the address tag of the incoming address and the stored address to make sure that this is the same block that we are talking about. Otherwise, there may be multiple blocks mapping to the same cache entry, and the one that is in the cache might not be the one that we are looking for, right? So when the address comes with the read control signal, of course, because this is a read access we are talking about, then the control unit of the cache should look at the index portion. It should figure out, it should know, the controller should know which bits are the index portion by design, right? We know the cache design is fixed. How many entries we have, what is the block size, and when we know that, you know which bits are the index bits. And you can use a demultiplexer circuitry to direct to the correct row or correct entry in the cache using the index field. So for example, if the index field was 101 in our example, it denotes this row, this entry, right? We have 8 entries in the cache and this is the one. Right. So then what happens is we perform the tag comparison at that cache, from that cache entry, right? So we extract the tag from the cache and compare it with the incoming addresses tag field using a comparator circuit. And we discussed the other day that we can use XNOR gates to build our comparator. Right. Then we had to make sure the entry is valid before determining that this is a hit. This access is a hit in the cache. So we take the valid bit and the output of the comparator circuit. If both are true, right? If the compare match is true as well as the valid bit is true, then we have a hit. Otherwise, we have a miss, and then we have to go to the memory. So while that is happening, at the same time, you can extract the data blocks from the cache as well parallelly and use a multiplexer to figure out which word you are referring to from that data block. In our example, we had two words in one block, 8-byte size block. So we had two words. So we can use the offset part, not the entire offset part. The entire offset part can be used to figure out the exact byte CPU is asking for. We only need a portion, more significant portion of it to figure out which word you need. So since we have only two words in a block, we need only the most significant bit, the single bit that is most significant from the offset field, and use it as a select signal to get the correct data word. And if we have a hit here, you can send the data word to the CPU, right? So if we try to fit this into our pipelined MIPS data path, once the address is sent to the memory, that is memory subsystem, it first reaches the cache. If we have a hit, we can send the data word to the CPU. All that can happen within one clock cycle, right? One clock cycle, we can decide the hit as well as extract the word and send it to the CPU. So that is all very fine. Now let's discuss a little bit more about it. So the comparator we discussed how to implement, and now we are going to discuss what is happening if this is a miss. If this is a hit, this is fine. If this is a miss, what should happen? So in the case of a read hit, we just have to send the data to the CPU and we are done. And we can easily do that within one clock cycle, one CPU clock cycle. On a read miss, what are the things we have to do? We need to go and fetch this missing data block from the memory. So we know that reading from the memory takes a lot of time. Several CPU clock cycles, 10 to 100 can be within that range, or even more sometimes, depending on the memory architecture and the communication architecture. So while this is happening, while you go and read the memory for the missing block, you need to stall the CPU, right? You can't let the CPU go ahead because the data that the CPU needs is still there. Otherwise, you will be creating data hazards. So you need to stall the CPU until the memory read is complete. So you need a specific, this direct map cache controller, it needs a specific signal to send to the CPU asking it to stall. And the CPU controller needs to use that signal, the stall signal from the cache. The CPU needs to use that to stall itself, right? To stop it from fetching further instructions and letting the pipeline go ahead. So it needs to completely freeze, right? Okay, so first thing is to stall the CPU, then make a read request to the main memory for the block, right? Remember, the cache and memory deal with blocks. They trade with blocks. While the CPU asks for words usually, or bytes occasionally, the cache and the memory, they deal with blocks. That is to support this exploitation of spatial locality of programs, right? So in the case of a read miss, the missing block, the entire block is fetched from the main memory. So you need to send the block address to the main memory and wait until the memory responds. It will take some time. It will take several clock cycles. It can go up to 100 or even more sometimes. Clock cycles, CPU clock cycles, right? Now, once that read is complete, once the memory has provided the data and data has arrived at the cache, the cache controller need to update the cache entry, right? So update the cache entry has 3 parts. So far we have 3 parts in our cache structure. One is the data block. You need to go and update the data block. You need to go and update the tag field corresponding to that data block, right? The block use the block address of that data block and extract the tag field from there and save it in the tag field of the entry. Then set the valid bit of that cache entry to denote that this is now a valid cache entry and the CPU can use it. Right. So 3 things to do when updating the cache entry. Then send the data to the CPU. Now we have the up-to-date data in the cache and we can send it to the CPU and clear the stall signal, right? Put the data on the connection bus, connection lines, and clear the stall signal so the CPU can resume its operation, right? So the CPU needs to keep monitoring the stall signal that is coming from the cache controller, right? So from the CPU side, if you look from the CPU's perspective, it doesn't know that there is a cache and another memory behind it. CPU sees this memory hierarchy as the full memory, the only memory that it can access. So in the memory access step, CPU has to deal with this stall signal and make sure if that stall signal becomes high, you freeze the operation of the CPU so that it waits until the memory read is completed. Okay, right. Now we have a little question here. We have a little problem. What about the old block that was in the cache when the miss occurred? We tried to read from the cache and it was a miss. Most likely it would have been a tag mismatch, or it could have been the valid bit was not set as well, right? One of the two or both. So what do we do with this old data block now? We have a little problem here, right? Do you see the problem? Can we just overwrite that old data block? Can we just discard it and forget about it? Is that fine? Right, so there is some missing piece here, and that missing piece comes from the writes, right? So we had discussed the write accesses and how they are handled before we go and discuss about that old data block, what happens to the existing data block, right? Okay, so we'll just put that question on hold for the moment and we'll discuss about write accesses now. Okay, here is our cache again, and we have an incoming address. So I think Dinidu is saying if not valid, we can replace that in case we have to store the data in the other case we have to store the data. Yeah, we'll discuss that. You're correct. Right. Okay. Right. Now we have our cache and there's an incoming access with a write, right? This is a write access. So what are the other signals accompanying this write access? We need the data word, right? The data word that is going to be written to this particular address and the write control signal coming from the CPU control unit. So these are the 3 things that the memory receives or the cache controller receives, right? The address to be written to, the data that you need to write to the address, and the write control signal. Now, as before, we had to use the index field to figure out which cache entry we are talking about, right? So the combinational circuitry, which is basically a demultiplexer, will use the index field to point to the correct cache field, cache entry. Then, as before, we had to perform the tag comparison and the valid bit check to decide whether this is a hit, whether this is the same block that the incoming address is referring to. So we perform using the same circuitry we used in the read. We perform the same set of operations, right? We extract the tag from the correct cache entry and compare it with the incoming addresses tag, and extract the valid bit from the correct cache entry and compare it with the output of the comparator to decide whether this write access is a hit or a miss, right? Exact same thing as in a read. Now, the writing. What we have here in the input interface of the cache controller is a data word, right? We have a data word and we need to figure out which block, which word in the data block that this address is referring to, right? So we have the incoming data word and this offset tag from the incoming address. So we use the most significant bit in our case because we only have 2 words in the block. If you have more than 2 words in the block, then there will be you need to use multiple bits, more significant bits from the offset, right? So whatever the appropriate case based on the cache design. In this case, we only need 1 bit, most significant bit. We use that in this demultiplexer to decide where to direct this incoming data word, right, to this byte or that byte, right? So based on your NDNS and all that, we decide we use the offset signals correct portion in as a control signal to this demultiplexer circuitry, and we can direct the data word to the correct place. And this is all based on the write signal, right? So this operation is controlled by the write control signal, which is sent by the CPU, right? Okay. Can this writing part happen in parallel with the tag match? Tag comparison. Now in the read access, we said both can happen in parallel because we are going to read anyway, right? So if this was a miss, then we can just discard it, discard the outcome. Now, in the case of writing, it becomes a little bit troublesome. What if we write and tag compare at the same time and the tag compare becomes a mismatch? If it was the case that this was invalid, then it wouldn't be much of a problem. But if this was the tag was a mismatch, if this was not a matching tag, then us writing to a word in that block is a big issue, right? We are corrupting data. So we can't really go and do that in parallel. We had to have some other mechanism to handle that. So let's go and look at that. Right. So in the case of a write hit, it's fine, right? We can write into that data block, write the word into the block, it's fine. But we need to decide, we need to know that this was a hit to do that. Let's deal with that later. For now, it's fine. Now, after writing, the block in the cache is now different from the one in the memory, right? Assuming that this address was a hit, this access was a hit in the cache, we went ahead and written the word into the block. But now that block, the version in the memory is different from the version in the cache. Yes? Is that okay? Is that clear? Version in the memory is different because we had a copy in the cache and we changed part of that block. Right? So we have two different versions now in the memory and in the cache. They have different data values. We call that the cache entry is now inconsistent with the memory. The entry in the cache is inconsistent with the memory. They are not the same, right? They have differences now. So how do we handle that? This inconsistency creates issues for us. So how do you handle that? One possible solution is always write to both the cache and the memory. Always go ahead and write to both the cache and the memory, right? Without writing just to the cache, you write to cache and at the same time write to the memory, or ask the cache controller to write to the memory. So in that way, we can avoid this inconsistency. This is called write through. This policy or this mechanism is called write through. This cache is of type write through. The write policy is write through. So this is very simple, right? When you get a write access, you write it to the cache. After checking the tag comparison, you write it to the cache, and then you go and write it to the memory as well. So both versions are up to date and consistent, right? So we'll discuss more about that as we go on. We'll just establish the certain concepts before we move on to the details. Now, what happens if this is a miss? Then we have to do something like we did in the read access. We need to store the CPU, ask the CPU to freeze for a while, go to the main memory and fetch this missing block and wait until the memory responds. Once the memory responds, you can update the cache entry. And updating, you know, there are multiple parts: updating the cache data block, tag, as well as the valid bit, and then write the new data word to the cache entry and write the new data word to the memory, because the only write policy that we know so far is write through. Let's assume that we are using write through, right? So fetching from the memory is the same as in a read access. You store the CPU, fetch from the memory, and update the cache entry. The added parts are you need to do the write to the correct word in that block, and you need to write the word to the correct block in the memory as well, right? So far so good. Now we have some solid mechanism that will work, right? It might not be optimal, but it'll work, right? Now again, we have the question, what about the old block? This was the same question we raised in the read access as well, right? When we bring a block from the memory and try to put that in the cache entry, which was a miss, which we had a miss on. What about the old block that was already there, the existing block? Now, what can we say? Do we have answers now? We had a miss. This is the question is true for reads and writes both, right? We had the same question in read accesses. We had a cache miss, be it read or write. Then we went to the memory and fetched the missing block. Now we are going to overwrite that cache entry with the new block. What about the old block? Is it okay to lose it? Now we have added this write policy into our picture, into our cache design. We have a write policy which is write through. With that in the picture, now is it okay to lose that old block, discard that old block? What do you think? Yes, it's okay. Why is it okay? If it was not valid data, okay, we can say it's fine. If the miss was caused by a tag mismatch, yes, exactly, because that data is available in the memory as well, right? Because our write policy is write through, we always write to the cache and the memory at the same time, right? For every write access, we update the cache as well as the memory. So losing the data block from the cache isn't a problem for us because the up-to-date data is available in the memory anyway, right? So if future access wants to access a data word in that old block, the correct data is available in the memory and that can be fetched into the cache again, right? So now with the write through policy, yeah, it's fine to discard the block. We can lose that block because the data is available in the memory, so we can depend on the memory for a future access, right? Because this our write policy is write through. Now with that, remember the problem we had, whether we can do the tag comparison and writing for a write access at the same time. Shall we go back to the slide here? Here, can we overlap the latencies of tag comparison as well as data writing? Now with our write policy, we can, because if we have a hit, there is no issue. We have already written the data word to the correct block and it is a hit. Fine, and we have saved some time as well, which is fine, right? Which is good. So if this was a miss, then we are going to go to the memory and fetch the missing block and replace this old block. So we are going to overwrite this anyway, and the correct version of that old block is available in the memory anyway if we have used the write through write policy, right? So in both the cases where you can have a hit or a miss, it's fine to overlap the time of writing, right? Overlap the time that it takes for the data word to go through this demultiplexer into the correct word and update the cache entry the whole time. That time along with this extraction of data from the tag from the cache and the tag comparison, right? So it's fine to overlap that time. We can do writing and tag comparison at the same time in the same clock cycle if it takes multiple clock cycles for a miss, it's fine. In the first clock cycle, we can do both these operations at the same time. Is that clear? Is that concept clear? Right. So let's move on. So about the write through policy, it's very simple to implement because it makes the implementation of the cache controller simple. It's a straightforward operation. Write through, you always write to the memory as well, right? Very simple. You just need to send the write access to the memory. And it in other aspects also, it makes the cache controller simple. You can overlap the times of tag comparison and writing, and you can not worry about the losing of the existing block. That makes the cache implementation very simple, right? Your cache becomes small and simple, which is in line with our main design principle, right? So the issue is it generates a lot of write traffic to the memory. Every time you have write access, you go to the memory anyway, right? So as we know, memory takes several CPU clock cycles. It takes a long time to read, and it can take a long time to update as well. Usually the read time is the slower, the longer one, but writing can also be slow, several clock cycles. Then it becomes inefficient when the CPU or the program running on the CPU has a lot of write operations, has a lot of store type instructions, store words or store bytes, store type instructions, right? If your program running on that CPU has a lot of store instructions, then this write through write policy is not very efficient. It becomes inefficient when it generates, because it generates a lot of write traffic to the memory, and it takes a long time. And the CPU has to be stalled all this time, right? Every time you get a write access, your CPU needs to be stalled, because every time you get a write access, you go to the memory anyway, right? Unlike a read access, every time you get a write, you go to the memory and you need to wait until the memory operation is completed. So a memory access usually takes about 10 to 100 CPU clock cycles depending on the implementation. So for every write, you need to store that many cycles your CPU, right? Which is going to be very inefficient for us. Imagine when we were discussing the pipeline, we tried to reduce stalls, even 1 or 2 stalls. We try to come up with different mechanisms to reduce those stalls. Now we are talking about introducing or having so many stall clock cycles. It doesn't add up, right? So what can we do to avoid this? Any idea? What can we do to avoid this situation? So Dini has answered, we can write to the memory if we want to replace that cache block with different data. Exactly. Yeah. So that becomes a different write policy. We will discuss it in the next class. Okay. So we'll stop. It's already 10. So we'll stop here. We'll pick up from here on Monday.